Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash into the home of someone who got a bit irritated. We interrupt this commercial to bring you this important message. It has come to our attention that many design teams suffer from non-automatitis or scriptophobia. These have been known to cause headaches and respin regurgitation. If you experience these symptoms, contact Semaphore for a no-obligation checkup. You don't have to suffer. Reach out to Semaphore. We now return to your regularly scheduled commercial.
Good afternoon and welcome everyone to our keynote presentation. Again, my name is Vanessa Cooper from Verlab and I am your general chair this year. And I truly hope that everyone has been enjoying the conference so far. It is my great pleasure this afternoon to introduce our keynote speaker. Manish Pandey is Vice President R&D and Fellow at Synopsys and an Adjunct Professor at Carnegie Mellon University. He completed his PhD in computer science from Carnegie Mellon and a BA in technology or a BS in technology and computer science from the Indian Institute of Technology, Kharagpur. He currently leads the R&D teams for formal and static technologies and machine learning at Synopsys. He previously led the development of several static and formal verification technologies at Verplex and Cadence, which are in widespread use in the industry. Manish has been the recipient of the IEEE Transaction and CAD Outstanding Young Author Award and holds over 24 patents and refereed publications. Manish, thank you so much for doing the keynote this year, and I would like to hand it over to you.
Vanessa, thank you. Okay, so let me start sharing my screen. Okay. This is visible. All right. Okay. So Vanessa, thank you. So, I wanted to talk about intelligent verification and how AI and ML is revolutionizing verification today. But to set a bit of context, we are in this era of, SysMoore. Really, this is about how Moore's law, has been the driving force for the last 50 to 60 years. And how we are seeing an exponential growth in the number of devices out there. And it's not that we're just going to actually, 3 nanometer, 2 nanometer and smaller devices, but also, this, system on chip and, and system on chip and actually, and, multi-die, systems that are being built today that is kind of taking us to the path, where, in the next few years, we'll have ordinary SoCs, with over 100 billion transistors, and huge software content. So if we look at it actually today, I think we no longer want to think of these chips just as isolated chips, but these are really parts of systems. These could be consumer systems, for example, the phones that you use, everyone is using today, or this could be complex data center MLAI chips, or you can also have applications, like self-driving and other, self-critical applications. Now, one of the things is that as the chips are getting complex, as the systems are getting complex, it's important to see, which is the direction that we are heading towards in terms of how fast the systems can be built, how cheaper the systems can be built, and when we are verifying the system, especially how much the quality of this verification can be improved. So one of the striking graphs today that we cannot see is that, over the last few years, the verification cost is growing exponentially. So the cost of verifying the hardware and software of the system, in 2024, a mid-size SoC was about 300 million. And in the next few years, this is going to grow to about 600 million. So this is actually a big portion of a design cost of any kind of create a chip today. Now, if you look actually at how, it's not just the cost, but also how much does the verification time dominate this verification. And now 80% of a chip schedule, in the future is going to be dominated by the complexity of verification. You have this, 100 billion transistor chips, and then you have to verify every single component of this. You have to verify every single state transition, and you make sure that these are kind of taped out correctly in the first step A. So this is actually a staggering cost of that we have to kind of pay. So definitely, definitely not cheaper, definitely not sooner. And I think also, and if we assume that the number of bugs, per million devices stay constant, then definitely not better QOR. Okay, so that's the kind of era that we are kind of heading towards. Another way to kind of look at it out here is that if you look actually at the hardware design, so that is kind of progressing, for the foreseeable future is going to progress at the rate of, growing 2x every 36 months. And, if you look at actually the hardware design productivity, design and verification productivity, that's kind of more flattening it out. And, using IP and memory to some extent, this curve is, ameliorated somewhat. But really, we have to look at other techniques really to kind of close the gap between what the hardware we can design and what the technology gives us today. Okay. So, question is, can we speed up verification by a factor of 100? Can we get a sooner, time to return out there? Can we reduce the cost by 10x? And 10x would be in terms of the number of tests that we write and the number of verification engineers that we hire, 10x in amount of compute resources that we can affect. And the last part is important because if you look actually at the bulk of the compute resources that are, that are spent today in the, by leading design houses, that's actually dominates the IT cost by what, by over 90% of that. 90% of the cost is from the server cost. Now, last question is, can we improve the QR by 10 percentile? Now, 10 percentile might not seem like much, but to take a design and kind of go from, 88% coverage to 90% coverage is a hard task. And I'll discuss it a bit later on there. To take a design where you can formally verify, for example, 80% of the properties to, for example, 90% of the properties that you're talking about, actually solving exponential problems. And this can take the longest, that there's a hard problems, and that can take, a huge amount of effort, 10 to 100 to 1000x more compute and more time and resources out there. So let's take an aside out here and let's see actually, what is it that we could kind of do by what's available in the world today that we can kind of look to improving and getting the results. And, we, hardly any of us are unaware that, that we have actually a machine learning revolution that has actually in the last 10 years has given us unprecedented results. So I've taken some of these, widely known problems out there today and kind of reflected at how, deep learning has changed, advances in machine learning algorithms and methodologies has changed us today. So for example, on the top, we have this ImageNet problem. We have this, we have hundreds of thousands of these labeled images. And the problem has been to recognize, what does each image represent? Is it a cat? Is it a dog? Is it a car? Is it a house? And, over the last few years, actually around 2014-15, there has been actually a big revolution by terms of deep learning, where now the performance, the accuracy of these neural networks, in fact, pretty much comes close to or even kind of surpasses this human performance. This is in recognizing these images out there and what these images are for. Another example is this speech to text conversion. Now, this has actually been a problem that has been a long-standing problem, right from actually, doctors' message transcriptions to, just about any phone transcription out there. And there have been a lot of different approaches that have come, but again, deep learning has revolutionized this field. And actually going from deep speech to different deep neural network to wave-vec to spec argument. This is actually basically LibreVox library out there. But again, Now the accuracy of speech to text conversion today exceeds human performance. So this is actually again one of the milestones really in machine learning that has been achieved with the techniques today out there. Another interesting area is this is in NLP, and we'll talk about one interesting application of NLP actually again in verification toward the end of the talk. And this is about how can systems, how can a deep learning help answer questions in English language from passages. And so this happens to be an example from something called SQUAD, Stanford question answering data set out there. But again, actually advances in these techniques using transformers and other techniques, has really brought us to the place, where average human performance, is exceeded by this automated techniques out there. And this is just not related to just limited to SQUAD, but we have NQ and many other open data sets today. So the question is, can we kind of leverage some of these advances that we see today in this machine learning, for solving, some of the hard problems that we face in AI today? I mean, for those who have not seen it, you should certainly go and watch our CEO's keynote address from IWSCC. He has very eloquently covered how machine learning indeed is revolutionizing just about every area of EDA, right from verification to place and route and beyond. But I think here in my talk, I'll be focusing more on the verification aspect of things. So at a very high level, I think that in EDA, we have different classes of machine learning. There's supervised learning, unsupervised, and reinforcement. I'll talk a bit about these, but these are broad classes, and of course you can have a mix of these. You can have semi-supervised or weakly supervised, many different variations and flavors of this. But these are kind of some broad access control, and this is what we have used in many of our tools that we have built here in Synopsys very successfully in improving, the performance of the tools. So a very quick detour into what supervised learning is, for those who are not familiar, so that you can set the context for future slides. And in supervised learning, essentially, we start off with this raw input data. And after that, what you do is that there's a training data set, and we have a model out there that we train the model to learn the patterns. And essentially, you have a data set where you have, in this case, for example, these are actually, pictures from ImageNet out there, and corresponding to every picture, you have the labels. Essentially, we have a deep learning neural network, which learns from this training set and learns what label does each of these pictures correspond to. And so the key thing is that you need a label data set out there, and I think somebody has to create this. And then once you do this, then the model kind of can take any other input and then kind of give you a set of outputs out here. And in this case, in case of ImageNet, for example, really the task is to find a classifier such that the classifier can take all the pixels of the image and then kind of give you the category, what does a pixel represent, which category of object that pixel is in. And it's really an optimization problem that kind of learns, and a lot of different techniques to kind of learn this. So this is one important technique that we use in EDA, except that this may not actually in verification domain. It may not necessarily be images. These could be, simulation vectors. This could be design design DAGs or abstract syntax trees. And I think from these, we kind of have labeled outputs as to, for example, different aspects like hardness of verification, or, coverage targets, or whether or not this problem, meets any cover point or there. So we kind of, we create a label, just like ImageNet, we have our own label data set there. Now, the thing actually is that unsupervised learning is the case, where we don't really have any target attribute. And this is about finding the intrinsic structure in the data. And it so happens that, in EDA, if you look at EDA out there in the verification flow, there are a lot of different data points that are generated across the flow, a lot of different design types. And we don't really, have, either the time of the resources or given the wide variety of data to kind of start labeling each of these. And so, but again, what we have discovered is that looking at patterns, looking at the structure of the data gives us a lot of interesting insights. And in fact, with some examples, I've shown how this can result in substantial time reduction for some of the problems that we have seen. So essentially, you kind of take this data, you have data which is not labeled, and you try to identify clusters in the data and which points are similar together, and and that and then ascribe some kind of meaning to it. Here, of course, we have shown a 3D point cloud, but it doesn't have to be 3 dimensions. These the kind of dimensions that we run into some of the problems. These are hundreds to thousands of dimensions in which we try to identify a cluster. Now, the last part, which is very common again in EDA, this reinforcement learning. And of course, everyone is familiar with AlphaGo Plus. I mean, there's another game playing programs which have employed reinforcement learning. But in reinforcement learning, essentially, you have your inputs, and you have an agent which tries to learn, given the input and given the state, which direction should be, what is the next step that you need to take to solve your problem. And so, for example, this in simulation, it could be that, what is the next, what should the output distribution be, or which is the variable to kind of change, which is a simulation pattern to generate. And based on the state, one gets a feedback, one gets a reward whether or not that move was in the right direction. If you're, it's just like thinking of if you're playing the game of chess, whether or not that move is going to get you, how close does the move get you to be checkmated, and obviously you want to not to do that move. So knowing the reward, knowing the penalty, you try to learn the sequence of actions to take, in trying to solve a problem. And again, very, very useful again in a variety of settings out there. And again, I'll be discussing some of the cases out there. And so essentially, you want to learn the sequence of decisions that maximizes the reward for covering, for example, coverage of a design, simulation coverage of a design. So these 3 techniques are pretty predominant out there, and in solving this problem out there. And I think that we have actually made used all 3 very profitably to kind of solve a variety of hard problems. Okay, so let me build this one out here. And again, so let's kind of again take another view of of this verification problem. So as we go into this verification, the sequence of verification is that we first start off with, for example, an RTL. We do a set of static checks. These are electrical checks, clock domain checks, or the structural and functional checks. These have a number of bugs. Fixing up bugs at this stage is fairly easy. Once you've done that, then we run formal verification based on the assertions and the properties we try to verify, and this brings out the next 20% of the bugs in there. The next step actually is simulation. Simulation actually is, again, the mainstay of verification. Most verification methodologies are there, and this kind of gets you about 65% of the bugs are there. And the remaining is actually when you run through hardware software accelerators like emulation or prototyping, which gets you the last 5%. As you go from the left to the right, it becomes increasingly expensive to get to detect a bug. Static verification, you can kind of get you can detect it right away. There's no test benches to write. Anything right. Informal verification, you have to write some initialization conditions instead of the initial state, a little harder. Simulation, let's see, your simulation requires it to actually have a full-fledged test bench, and hardware accelerator, of course, is more expensive. But none of these, the bugs detecting in any of these, the cost is far lower than the cost of detecting a bug in post-silicon and silicon lifecycle. Okay, so let's see, how do we, so what makes this complex? What makes application of verification machine learning to this complex? So if you look at actually, about an SoC in about 2 years, they'll have about 100 billion transistors, about 1 billion state elements. And that translates to 10 to the power 300 million states. And just to kind of give us an interesting comparison, if you look at the number of atoms in the observable universe, that is actually a tiny, tiny fraction of that, only about 10 to the power 100 atoms in the observable universe. So the kind of states we're talking about is you know, it's incredibly large. And we have to model these, you know, using machine learning algorithms, and we have to kind of get valuable insights and, you know, and make decisions to make this problem solve efficient. Now, if we look at actually the verification flow, there are diverse verification formats and tools and flows. You know, you have C+ models in C++, or you could have system C out there, or you can have system Verilog, or system where, and you have system Verilog assertions, you have covers, and you have reports. Now, compounding that, you know, as, you know, EDA tool developer, you know, we have access to all internal representations, and some of these actually are pretty insightful, like, you know, like, for example, abstract syntax tree. Now, unlike, for example, many of the large, well-known popular problems, there's no verification ImageNet, there's no verification squad, so there's no standard, you know, standard label data set that we can kind of refer to. So, you know, I think that one of the things that is there in, you know, in EDA, which is very common, is that we have relied a lot on, you know, of course, we still use supervised learning, but we have relied a lot on unsupervised and reinforcement learning to solve some of the hard problems that I'll be talking about shortly. Another problem actually is that the data is highly variable, right? So these are really graphs. All of these things are graphs. There are no fixed size images or word embeddings. And with every design, you have a different kind of graph. There have been obviously some recent publications which have, you know, which have learned semantic representations of these graphs to reduce these to fixed size embeddings. But, you know, but working with graphs is again harder than working with fixed size image patches or fixed size vocabulary words. One last but subtle point is in the challenges in machine learning is inference speed. Now, when you do inference and when you have to make a decision, now, depending on how coarse-grained the problem is, if the algorithm that you run after making the decision, you know, takes a few minutes, taking a few seconds of inferencing does not hurt. But if the algorithm that has to run runs in milliseconds, the inference has to be done, you know, in fractions of milliseconds. So so the kind of models that you can deploy has to be very carefully thought out as to when it has to make, you know, as to how it can kind of improve the performance system. So we have to think of all of these different things actually when we make, you know, when we think about, you know, applications of machine learning for verification of problems. Okay. So now, if we look at actually verification from a verification and from a simulation perspective, manual and random verification, setting manual patterns and random simulation, right? That kind of gives you, you know, gets you some coverage target, and obviously the coverage target, if this is the coverage target, the green line, that stays pretty far down. And so it's very common to kind of do constrained random and get closer out there. So the question really is, can we do better with AI? Can you get to the coverage target sooner? So for that, we want to kind of look at this, that if we can accomplish this, then our time to result, of course, you know, is smaller out there. We can accelerate this out there. We can get perhaps in the same time better quality of result. And I think that, of course, you know, the compute cost, right? So we kind of reduce the cost of compute out here by saving this, you know, by saving this time out there. So by accelerating this, you know, by learning and by shifting left, there are a lot of advantages to be had from this. So let's look in the context of VCS, you know, how does this kind of play out with some of the recent advances? So these are, you know, this is about the problem of verification space exploration. So each of these dots refer to a design state. Now, these red happen to be legal transitions. So between these designs, obviously, not every state can be reached from every other state. So these are the legal transitions. Now, given VCS and given the constraint target and tests, So a set of the states are coverage target, and our desire is how can we get to, how can we kind of cover all of as many targets as possible in this. So given these constraints and targets, the VCS, runs simulations, a set of tests are run, and then it can go through these targets, which are kind of painted green or encircled with this green squares up there. But problem is that, and then the thing is that let's say a bug is found here, but now the problem is that there will be areas where you'll have coverage holes. And so that is represented by the gap between what the desired coverage target is and where random simulation, constrained random simulation takes us. Now, can we do better on this? So building this out there. Now, question is, can we learn from this coverage holes? And can we use AI to kind of do better? And it so happens that indeed we can learn these distributions, we can learn we can build a cost function, and we can produce better AI-driven constrained tests out there. And we can, in fact, find out bugs in this coverage holes. And for a mobile processor, and this is actually a real data out there, we not only kind of take this constrained random and do better than that out there. In fact, coverage target, this is actually a real use case again, where the TTR reduces from days to hours. And I think that using our mobile, using our AI, VSW.ai techniques, we can in fact exceed the quality of results, can exceed the target verification using it. So this has actually been an eye-opener for us. This is something that we have actually had in the works for many years, but this has recently yielded great targets. And this is a great example, where using AI we can not only get better TTR, but also kind of get better QR, and of course, get at cost of results. Another example actually is static verification. This contains a set of structural and functional sign-off checks. And these are checks for power intent specification, UPF checks, UPF specification checks, clock domain verification. You have hundreds of clocks in a modern SoC, which have, interact in different ways. We want to make sure that all of these interactions work well. A common mode of failure for chips. Reset domain checks, that's again very important. It's not just you have reset pin and you can reset it when you have multiple reset domains out there. And you want to make sure that these can play together nicely. And of course, you have language checks. And these are actually sign-off checks that is important for actually every design to pass before it moves to the next stage of verification. So now it's common for the static verification tools to produce, tens of thousands to millions of violations. A single, operator or a single specification issue or error, or perhaps a designer can result in millions of violations. And it's hard to kind of know for actually many designers, unless you're a very, very experienced engineer, to know where do you start debugging this hundreds of thousands of violations. So you have 340 fake violations, and actually this happens to be a real designer there. And now this is where we have actually very successfully used, unsupervised learning. I think we have actually, this has been actually refined over multiple iterations, but this is actually by using a set of, hierarchical multi-phase clustering algorithms. We can kind of identify which violations are related to each other. And we can cluster these related violations. And then we can also identify cause-effect relationship between violations, and then identify a root cause, a single root cause, for each of these different clusters, which causes the issue. Now, this happens to be, I think, really, for example, for a mobile SoC, where we have this design constraints, using VC Spyglass CDC, there are about 107,000 violations, unsync violations. And after doing this clustering, the total number of clusters for user review gets reduced down to about 102, actually, in fact, about 1000x reduction. Now, in this case, actually, looking at this example a bit more closely, just to kind of give a sense of a specific example, the user happened to specify a clock at this blue pen, happened to specify another clock at this red pin. And then he's specified, the user specified both of these to be asynchronous in the specification. Now, given the path out here, this is really supposed to be synchronous, and that kind of this fans out to a large number of flops and large number of crossings, and you get about 12,000 violations. Now, using this root cause analysis and using a clustering, this was all reduced down to a single cluster and a single root cause. Otherwise, the user would have to kind of look at all 12,000 violations. And obviously, of course, the user is expert. They could spend less time, but then you could reduce it down to this and get it, and debug this actually in a single step out there. Now, this is about 10 to 100x reductions in violations for analysis. You get the root cause. And an important thing is that you minimize the number of human waivers. So typically for every time you have a violation, a users kind of step in, they write this violation that, that you have this waivers to waive this check. And many times these waivers, in fact, waive out legitimate violations, and that kind of causes, again, failures in verification. So again, this is definitely actually a huge, time reduction, but also by eliminating waivers, improving the quality of results out there. Okay. Now, this is the case, where, through manual analysis, you get a substantial reduction in AI-based analysis and, time to result out here, using, AI for static verification. Looking at actually another problem, this is about formal verification, right? So this is actually, an important verification technique, where, given a design and given an assertion, rather than use simulation, analyze through a set of different techniques, analyze the state machines comprehensively, and then decide, and determine whether or not these properties hold true under every condition. Formal verification actually has, as a field, has seen, tremendous, advances in the last 20 years. But the size of the designs also keep on growing, and I think that despite the despite all the advances, this remains a very hard problem. But the advantage of it that you can get complete verification. So the challenges that we have today, there are hundreds of thousands of properties. Where VC formal, for example, we use about 30 plus different engines and solvers. We have a fixed number of machines, right? And with hundreds and thousands of properties, even if we give each property about 30 minutes to run, this is a long time. This is actually many days, many weeks out there. And given this compute resource limitations and given this time limitations, this is something that very quickly becomes a very challenging problem. So what we've done actually is that, given these different properties, we go through this ML optimization step, where we can order the properties in a spec route. We can assign properties, which engines run and in what sequence, and how much time do we give to each of these different engines. And then we dispatch this, engines. Then we dispatch this properties to engines to run in the cloud or in the data center out there. And in a way, this employs reinforcement learning to learn and make the right decisions. And again, there's a cost associated with making every wrong decision out there. And given this we have seen again a great, I think this is actually for a recent SOC, this kind of gives us a tremendous speed up in this performance out there. And compared to default scheduling, we get a reduction of time of about 10 to 100x out there. And I think that again, it's not just reduction in time, but just because we can get results sooner, we can kind of get extra QR by taking the extra time to verify these properties. So again, a reduction in time, reduction in cost, and I think that better results out there. Now, one of the problems is that you have done your formal verification or you have run your simulation. Now, obviously, we'll be running into many violations. Now, what do you do? How can you debug these efficiently? For example, in a tool such as Verdi. So we have actually millions, billions of signals. Simulation runs with millions of cycles. How do you trace back a violation in time and space? So which time a window to look in, which signals to look in into this there. And again, we have actually applied machine learning techniques to this problem. And I think that we have using debug root cause analysis can kind of very efficiently do this. So by looking actually at past verification, past simulation results, and look actually at debug action graphs, we can do ML-based analysis. It's a combination of unsupervised and supervised learning. We can find out, what are the top root causes and where do this lie design and which time window they are in and where the bug lies using our ML debug assistant. So this kind of speeds up again the debug process considerably and helps, even for bugs that we discover, helps the user trace back and find out what the issue is. Now, again, this is compared to manual debug, get a substantial gain in TTR using this reset debug analysis technique. So now we have seen actually, that each of these, using machine learning for each of these, we can kind of get improvements in QR, TTR, and COR, and and definitely machine learning kind of helps this, and then debug kind of helps again kind of close the gap out here for all of these different tools. Now let's look at another aspect of there. Now, an important problem in verification is how do you take a circuit specification to a system Verilog assertion. This work actually was published in KDD very recently. But the problem here is that IP engineers create this verification items manually. They kind of create a specification document. And this specification document specifies different conditions. So for example, that a signal is permitted to change only when it receives an acknowledgement within a certain time, and other English language statements. Now, one of the advances actually that I wanted to kind of highlight a bit early here, but I think one of the advances that we've had is that using deep learning and NLP techniques, we can read the specification document, detect sentences, analyze these, translate these into system Verilog assertions. So it's magic actually that you can take English language and again, you have to be careful about the kind of writing style of these properties, but actually generate system Verilog assertions. And I think this is actually a great time reduction, and I think great labor savings out there. And I think that we have done with real world, measured this with real world QR metrics, and with iterative refinement of the user feedback. This has actually kind of improved, and I think has turned out to be a very valuable tool in this on the overall verification process. Now, we have done all of these different things. We can kind of take static formal, simulation debug, kind of run things efficiently. But I think as a part of any modern chip verification methodology, we constantly run regressions. And everyone who runs regression knows that there's so many redundant regressions that are run, whether it's your smoke test or whether it's a nightly regression. When you want to do a check-in, how many tests do you run? And I think we have actually, again, developed intelligence test selection, but really I think this has been about, how do you use machine learning to select the right set of RTL tests so that with every check-in, you can kind of get a higher degree of confidence that, yeah, you have covered the functionality in all of these tests, for example, with a recall of say 90%. And this whole process is that we can extract or take the data from, from all the different repositories, from the bug databases, from the, from user bugs out there, extract our data from the design, from the front end, from the compiler, from the abstract syntax tree, and learn this design data over time, and then kind of have this ML system, which can then, for example, out of 1,000 tests, identify the 100 tests that you need to kind of run and get pretty much cover all the features that you'd like to do. So for example, you make a single line of Verilog change. You don't have to run all 1,000 tests, perhaps you don't only 100 and get the same coverage. So again, a tremendous savings in the amount of time and efficient use of your compute resources. So this is one of the examples actually of using ML, how we kind of simplify the overall verification process. So now, the question actually that you had was that, can you speed up verification by about 100x? Can you reduce the cost by about 10x? And can you improve QR by about 10%? And actually the answer is yes, an emphatic yes. So closing, some closing remarks out there. So we have leveraged deep understanding of problems. So we understand these problems and their characteristics and internal data representations. And many of the solutions that we have talked about actually, in fact, have gone through multiple generations and multiple iterations of refinement before which we have seen success. But leveraging this deep understanding and this ML advances the last decade, we have actually succeeded in applying these very successfully across our full verification suite, be it static, dynamic, formal, debug. We have interesting applications on analyzing, creating design specifications automatically. Again, I should warn you, it's not everything you can do, but I can give a limited, given actually prescribed data specification formats, we can do it fairly successfully. And then obviously the intelligence test selection lets you optimize your runs and optimize your IT resources. Leveraging this deep understanding of problems and ML advances, we can get an order of magnitude gain, in speed up in runtime, in reduction in cost, and and I think at least a 10 percentile improvement in quality of results. And the last 10 to 20% really gain is the hardest today, as any verification engineer will testify. So this actually, we are moving now to the era of 24-hour design cycle. We are not yet there. We are definitely but moving in the right direction. That's a part of the vision of ERI, or this idea. More breakthroughs are needed in design and verification representations. Talk about how our designs are all in variable size. But again, if you look at actually some of the language models that are there today, we have GPT-3 and other T5 and other great models out there. Now, what we've had are protocol language models. Every protocol talks, has its own vocabulary and its representations. And this multi-billion, parameter models can very well capture these and be nice generators of stimulus out there. Some recent work actually from Google Brain has talked about semantic design representations, where they kind of talk about taking control, data flow graphs with the coverage and having, and actually, in fact, interestingly represent these as fixed size vectors. Again, graph applications of graph neural networks, which can give us this fixed size, vector representation with which to reason about these problems. So that's actually, again, a great breakthrough. And I'm sure there'll be others that will be coming us, but these data and learnings have given us a good head start to kind of realize the dream of a 24-hour design cycle. Thank you very much.
Thank you, Manish. That was an excellent presentation. I want to encourage everyone, if you have questions, please use the Q&A in your Zoom menu, and I will go through those. I'll start us off, though. You mentioned design size. One of the key components for machine learning is having, a large data set. Is there a design that is too small where using ML techniques could be, inefficient at that point for closing coverage or test selection?
Okay, so a design, so it depends on the kind of problem, actually. So for example, actually, we have seen some small and very challenging designs for formal verification. And certainly, I think we've seen that, using some of these ML techniques there has helped us verify, verify those designs efficiently. And in fact, you can have actually a 200 flop design, and that will kind of, depending on the kind of design topology, could stretch the limits of formal engines, and those can certainly help in solving these out there. But again, if you look actually from a simulation perspective, simulation really kind of scales up to much larger designs, tens, thousands, hundreds of thousands of gates out there. So you'd want to definitely use this for larger application. But now, in fact, these techniques kind of spread out across all design sizes.
Okay, going to our Q&A. For formal, does ML select engines only, or will it also apply to, or will also apply ML to formal verification algorithms?
Yeah, Hamid, that's a great question. So, so definitely, selection of engines, runtime for engines, that's one of the problems that I presented today. But but again, decision making within the engines can also be done by machine learning. But one of the things that's very important to kind of understand is machine learning cannot produce the result itself. These results are deterministic. These results cannot be probabilistic. So probabilistic stuff can be used for decision making, but not for producing the actual result, which has to be deterministic and absolutely always correct.
Okay. And if you were to use ML for simulation only, would that be less efficient?
Actually, so we've talked about ML. Actually, this VSO is a great application of ML in simulation. So absolutely not. I think that it's when you're doing simulation itself, then VSO has been a great example actually of how ML makes simulation more efficient. I mean, again, I think I'm assuming this question is about simulation-based, methodology out there. If the question is, can ML be used within the simulator itself? Yes, again, there are many decision points within the simulator that can help in kind of heuristics to select maybe perhaps different algorithms within simulation.
Okay. Do you see any opportunity for applying ML to silent data corruption, SDC verification, and post-silicon debug?
So again, there are applications. This is, we have not specifically worked on this problem, but this actually appears to be more of a question related to post-silicon debug. And there haven't actually published work where you can look at actually, this, you run this post-silicon, you have this waveforms from post-silicon artifacts, and then you can use these to localize, use this to localize bugs and localize other problems out there. So definitely there are applications, but this is actually, I would say, a fairly nascent area.
Okay. Do you see Synopsys adding these machine learning features to VCS natively?
Actually, so again, this VSO again has been, I think, a great example actually of application of machine learning to improve simulation efficiency to kind of solve the problem of detecting bugs and improving your coverage. So certainly, ML has been a key part of our VCS usage methodology.
Okay. Since these ML optimization depends on data that, I'm sorry, the question is a little confusing.
So, okay, so question actually is from Balachandran.
Yes.
So ML optimizations depend on data, and data depends on design flow, CAD methodologies, toolset, and verification culture. So no, great question, actually. The thing actually is that we have worked hard in kind of creating, working, for example, with our internal design representations and to a great extent, kind of creating, what should I say, flow agnostic, flow agnostic solution. So for example, in let's say we take the case of form. Really, in the end, no matter what your flow is, you have to have a set of properties. You have to have a set of, you have to have some designs out there, and then we can kind of take a look at these and kind of verify no matter which flow you kind of come to out there. Now, in case again of static, for example, again, you have to have this set of, you'll have your RTL, you'll have your way of writing UPF or your SDC specification of a clock specification. And again, no matter which flows these come to, we kind of, these are unsupervised algorithms that they kind of work. Again, one of the concepts out here, again, is that how do you kind of learn on site? And I think that we have a number of tools which also do some kind of on-site learning. They come with warm models and then do on-site learning and kind of do this. But actually, our effort has been really to kind of create tools which work across, different methodologies. Only one thing I should say is that, see, again, as tool builders, we have access to a lot more data. We have access to the internal state of the tool. So that gives us, an advantage of making the tools to be flow and methodology agnostic.
Okay. As mentioned in one of the slides, we need past simulation databases for using reinforcement learning. Wouldn't we need to create a bug-free pass SimDB for each design that we need to verify? And wouldn't that be expensive?
Actually, we don't. So the thing actually is that we don't. I think that our engines kind of learn. They learn from the violations that they hit. We know when an assertion fails, and I think that we kind of also learn from how long does it take, for example, to kind of get to a specific cover point. So those are some things that are machine learning. Machine learning. Work out there.
When you're doing simulation in the tests and experiments you guys have done, have you seen a performance difference between like supervised learning per se and as opposed to reinforcement learning?
I didn't get a question here, so
I'm sorry, that was one of my questions. I just...
Oh, okay, sorry. Okay, I'm sorry. Go ahead.
No, I was just curious between supervised learning and reinforcement learning. When you've been running experiments, have you seen differentiators to which one is more impactful during simulation?
Actually, so what we have done, actually, we have been actually, what should I say, fairly tactical in the sense that we do a lot of different experiments, and we say that, hey, this technique works, it does really well, and we kind of apply it. So we don't race necessarily for the same technique, or for the same problem, try to apply, always compare to different algorithms. It just so happens actually that reinforcement learning is a great fit for many things that you do, because for many of the design flows, we don't have labeled data sets for supervised learning. So I think so many of the methodologies that we've talked about, that I've talked about today, or many of the flows that I've talked about today, really these are unsupervised or reinforcement, and in some cases, in fewer cases, supervised.
Okay. The next question is, how far are we now from applying AI to the goal of 24 hours certified FMEDA risk analysis?
Actually, I would say that we are closer than where we were maybe 2 or 3 years back, but we're still a little far away. So this requires changing our existing practice, changing the way we do specifications, right? We write, for example, there's so much diversity in the way we kind of create test benches, non-sensible test benches. So if we can standardize on these, where each of these can have well-defined semantics, where these can be easily be partitioned up, right? Then I think perhaps we can kind of go closer towards that. But design methodologies certainly would have to change to kind of go there. But I'd say that wherever we are 2 years back, we are, I think across in the industry, we are, an order of magnitude better today.
What's your opinion on how ML AI could help identify coverage gaps across static formal verification and simulation? Could we use ML AI to prioritize the remaining coverage space?
I think that ML AI could identify this other. I mean, this is something actually that, in any verification flow, this data can be collected, and I think a combination of supervised and unsupervised learning could potentially help this. We have not spent, we have spent limited time kind of analyzing this, but I think that given the limited analysis we do, it certainly seems, a problem that can be looked at. But one of the things I should kind of mention, everyone, is that none of these algorithms kind of come easy. This requires multiple iterations of understanding the data, understanding what models can capture this behavior and then get this working. But I think this is definitely a very worthy problem to kind of solve today.
Do you see any ML opportunities to self-tune test and simulation based on the types and categories of bugs that we encounter?
ML opportunities to self-tune tests. Not sure I follow. I understand the question. Self-tune tests and simulation.
I'll take a stab at what they're asking. I think they're saying if you have a categorization of maybe the bugs that you typically find in your type of domain, is it a way to use the optimization function to do test selection for those?
Okay. So I think, in fact, an interesting application of this is that, for example, actually in our in this debug analysis, root cause debug analysis that we have in Verdi, I think in fact, we try to take a look at these waveforms and violations and try to kind of classify tests into different categories of violations. And so I think those techniques are very certainly, it's a combination of supervised and unsupervised learning. So those techniques are certainly very much applicable to, that kind of debug problems or this classification of bug problems that could be kind of done. The challenging part in many of these problems is kind of identifying, given a set is first making sure that you have enough tests and making sure that what are the features that you're selecting to kind of get this. So, I mean, I think that if we are kind of, if the user actually has his own verification methodology, he can kind of, and verification flow, he can certainly have the right kind of messages, log files, and then experiment around with doing so. Definitely categorization of tests with violations would be something that could be, again, a problem that I can see could be easily done. Okay.
I think we have just a few more minutes left. I'll remind everyone, if you have questions, to use the Q&A and not the chat to ask them. For someone who's trying to understand this more and ramp up, outside of just using the tools, is there any recommended way you would suggest to do that, or recommended readings?
Actually, the first thing actually is that see, the two different what we see is actually two different skills that are needed actually in kind of make to understand this area. I mean, first is obviously the person has to understand the specific domain well. If you're, for example, working in simulation, you need to know simulation damn well in every aspect about it. But the other part actually is also actually definitely understanding actually a bit of ML and deep learning would be important. And again, there are lots and lots of excellent resources online, right? From just about every, whether it's a TensorFlow tutorial or PyTorch tutorial and Udacity and Coursera, and lots of online resources where one can kind of pick up stuff from and learn, learn these basic tools on there. So it's, if there's a separate message that can forward it to me, then I'll be happy to share some thoughts in more detail.
Okay. There have been a lot of presentations over the years at DVCon about AI and ML. Do you see an increase in the industry now?
Actually, not only I see an increased interest in the industry, but in the last few years, actually, I see more and more applications of this to solving some very, very hard problems and kind of solving these well. I mean, I think that you can look at, for example, many of the talks, by folks, not just by Synopsys, but across the semi-industry in solving hard problems in verification, hard problems in place and route, and others are there. So, and again, if you look at, for example, paper conferences like DAC or ICCAD, again, tons of nice, very, very nice papers, solving problems across, solving hard verification and other EDA problems. So definitely, I think it's something that's changing the industry.
Okay, I appreciate that. And we are out of time. I'd like to, first of all, thank you for presenting today. This was a excellent talk, and as we do see that increase in the industry, I think hearing about it more and more will help people come up to speed and understand what's going on. And I would like to tell everyone this session was recorded, so it will be on the platform, and we'll get the presentation from you and post it so they can view along with you, and they'll be able to add comments and questions to the page in the platform if there's lingering questions out there. So again, thank you so much for presenting for us this year.
Vanessa, thank you for hosting it. We enjoyed the talk. Thank you.
Thank you.
All right.